state, and the talk is going to be given by Kaan Genç.
Thank you. So, hello everyone. Today, I want to talk to you about data races. And specifically, I want to talk about why the existing methods of data race detection are not really enough, and why we need more powerful methods. And of course, how we achieve those more powerful methods in our work. And to do that, I first need to give you some background in race detection. So the most commonly used form of race detection today happens before race detectors. So these are things like Intel's thread sanitizer or fast track, which you might have already used. So what these tools do is that you run your code using these tools, and during the execution, if a race happens, they'll tell you whether the race happened or not. But the problem is that these tools are only able to detect races that actually happen, so conflicting accesses that are really next to each other. But the problem is concurrent programs are non-deterministic. You don't know how the execution is going to go. And a lot of races are actually very rare. They don't happen in every execution. They only happen in very rare interleavings of threads, which means that these tools will have a very hard time of actually finding these rare races. So to fix that, people have developed more different methods. For example, there are SMT-based approaches. So what these approaches do differently is that very simplified, they'll take an entire program execution, and then they'll feed that to an SMT solver, and then they'll ask the SMT solver, is there a data race in this program? And the SMT solver will answer yes or no. But there's also a limitation with these tools. So while these are extremely powerful, they can't really scale up to full program executions, because real-world programs have up to billions of events in them. So if you feed that to an SMT solver, the SMT solver can't really solve that. So another method that people have developed is predictive race detectors. So these methods are a lot more similar to happens before race detectors, and what they do is that if we take the happens before race detection formula and we reformulate it and change it in ways that instead of just looking at a single execution, well, we still look at a single execution, but what if we can predict other executions just by looking at that single execution? So I want to show you an example to explain now why the happens before race detector wasn't enough and why people developed the methods of weak causally precise and doesn't commute, the predictive race detection methods. So what's going on in this example is that this is an execution trace with two threads executing. And what's happening here is that we have some writes and reads to shared memory, and these threads are acquiring and releasing some locks. And everything that you see here is listed in the order of time. So things at the top are earlier, things at the bottom are later. And if you were to write some code that when you execute that code, you'll see an execution like this, and you run your code using fast track or thread sanitizer, these tools will report that there is no race here in this example. But is that really true? So what I'm going to show you is that there in fact is a data race in this example between the write of X and the read of X. And to show that, so first of all, why does happens before race detectors tell us that there is no race here? Well, the reason is because they look at these critical sections that we have here in between the accesses to X, and they say, well, both of these critical sections acquire and release this same lock M. So since they're acquiring and releasing the same lock, and these are in between these accesses, so they're in between the potential race, they say that, okay, there is no data race in this example. However, if you actually look at what's inside these critical sections, we have, so one of them is accessing this variable Y, while the other one is accessing some other variable Z. So these threads are not actually even accessing the same variables. They're actually accessing different variables inside these critical sections. So they're not really doing any kind of synchronization. They just happen to hold the same lock. So as a result, we can actually imagine what if there was a different execution of this program where the critical section in the thread 2 was pushed up and the critical section in thread 1 was pushed down. So this is completely possible because, again, execution is non-deterministic. The scheduler might just happen to pick thread 2 first, and the execution might go differently. Well, if that happens, we'll end up with an execution like this, where these critical sections in between the accesses to X are actually pushed out of the way, and the race is actually happening. So what we actually did here is that we predicted another execution. So based on the execution that we were just looking at, without any access to the source code or anything, just looking at the execution itself, we predicted that there exists another execution where a race does happen. So we call this a predictable race. By looking at an execution, you predict another execution with a race. So this example here has a predictable race. Now, happens before is unable to detect this, but weak causally precedes and doesn't commute are in fact able to predict that there is a race in this example. Now, my previous example showed you why happens before wasn't enough and why we needed weak causally precedes and doesn't commute. Now I want to show you a new example where that showcases why weak causally precedes and doesn't commute aren't enough and why we need more powerful methods. So this is a very similar example to the last one, but the difference is that now these critical sections actually access the same variable. Now, if we were to give this example to weak causally precedes or doesn't commute, they'll again tell us that there is no WCP race or DC race in this example. They don't find any races. And again, the reason why they're doing that is if you look at what's inside these critical sections, so these tools are actually looking in the critical sections, they'll say that, okay, both of these critical sections contain a write to Y. So they contain conflicting accesses, which means that we can't do that prediction thing where we push something up and push something down, because if we did that, these are conflicting accesses, the execution might go differently, we can't know what's going to happen. But what I'm going to argue is that that's not entirely true. Because if you look at these, so these are both writes to Y. So while both of these threads are writing to Y, there are no reads to Y. Nobody is reading what we're writing to Y. So it doesn't really matter which of these critical sections executes first and which executes last. Nobody's going to read Y. It doesn't actually change anything in the execution. Now, of course, you might say, but hang on a second, this is just a simple example. In real-world programs, somebody is going to read that Y. And that's entirely true. But what's important here is that even if you did have a read to Y somewhere in your program, when we're talking about data race detection, we only care about accesses that are leading up to the race itself. We don't care about accesses that are after the race. Because what we really care about is whether this race is going to happen or not. We don't care whether once that race happens, what's going to happen after the race. We're not dealing with that. We're just dealing with the race itself. So in this example, even if there was a read Y afterwards, we don't care about that. And as a result, we can actually do the prediction thing and predict that there's a race here between the accesses to X. Now, so clearly, weak causally precedes and doesn't commute. There are very simple races that these tools cannot find. So we came up with two new methods of race detection. Strong dependently precedes and weak dependently precedes. So these are our new methods. Strong dependently precedes is a provably sound method, which means that it finds no false races. And both in theory and in practice, we find that it finds more races than weak causally precedes, which is the state-of-the-art sound race detector. On the other hand, weak dependently precedes explores a different route, which is it's a provably complete method, meaning that it finds all races that are knowable from a single execution trace, which is unlike the prior works, weak causally precedes and doesn't commute. But the problem with weak dependently precedes is that it also finds false races. However, we actually have a method of filtering out these false races, so we don't actually have to report any false races. We only report the real ones. Now, it would be very time-consuming to actually go through all the details of how these methods work and what the differences are with the prior works. You can find all of those details in our paper. However, I want to show you some of the critical key differences between the prior works and our works. So, one thing I'll show you is what these methods consider to be synchronization, like what kind of accesses they actually say it constitutes a kind of synchronization between threads. So if you look at the same example, so this is the exact same example we were just looking at. So as I've said before, weak causally precedes and doesn't commute looks at these critical sections and says they have conflicting accesses in them. And as a result, we cannot do any prediction here. These threads are synchronized, there is no data race. However, if you look at strong dependently precedes and weak dependently precedes, they don't consider right-right conflicts to be synchronization. SDP doesn't accept right-right conflicts, and WDP goes even further and only accepts right-read conflicts and only under some circumstances. So as a result, these methods do not say that there's any ordering between here. So what that means is that they are able to predict that other execution where these critical sections are moved around. So strong dependently precedes and weak dependently precedes correctly finds the predictable race that we have in this example. Now, another thing I want to show you is what these methods consider to be the actual point of synchronization, because that's also an important difference. So to show that, I want to show you a different example. So this is a slightly more complex example, and what we have here is we have a write-read conflict between these threads. So one of them is writing to X, the other one is reading from X. And more importantly, we have this branch event. So this is something that weak causally precedes and doesn't commute hadn't considered before. So these are things in a program's execution, such as ifs or switches and so on, that conditionally change the execution itself. So they conditionally change how the execution is going to proceed. So if you look at, again, if you look at what's inside these critical sections, because that's what matters, since there's a write-read conflict, all of these methods consider this to be a form of synchronization. However, weak causally precedes, doesn't commute, and even our method strong dependent precedes considers writes and reads to be the points of synchronization. So they'll say that by the time we get to that read X in thread 2, that these threads are now synchronized with each other. And if there are any races surrounding that, that's not actually a predictable race. So the accesses between the write Y in thread 1 and the read Y in thread 2, all of these methods will say there is no race. However, WDP only considers branches to be the actual points of synchronization. And the idea behind that is that even if you read something, unless you're actually using it to do something, to change something, it doesn't matter, right? So even if you read X here, if there is no point where the execution can branch, that read Y is going to execute no matter what. So you might say, however, that, okay, there is in fact a branch here in this example. So what's the difference? Well, the thing is, as I said before, we don't actually care about events that are after a race. So this branch event here, we don't actually care about that because it cannot affect whether the read Y is going to happen or not. And as a result, weak dependently precedes, our method is the only method that can find the predictable race in this example. Now, finally, I want to show you two very similar examples. So the only difference between these two examples is the location of the write Y in relation to the branch. So on the left, it's before the branch, and on the right, it's after the branch. And that difference is actually very important because, so if you look at what's inside the critical sections, again, we have read-write conflicts, and we have the location of the branch. And as I said, the location of the branch actually ends up being very important because, again, we only care about things that are leading up to a race and not after the race. What that means is, on the left, the branch event is actually an event we don't really care about because it comes after the race itself. However, on the right, that branch event is actually before the racing event, right Y. So it is actually important. If we try to predict a different execution, that branch might lead the execution in a different direction. That right Y might not execute at all. We can't give any guarantees in that case. So as a result, the example on the left actually has a predictable race, while the example on the right doesn't, because we cannot predict it. So the interesting point here is that weak dependently precedes is able to find the predictable race in the example on the left. However, on the right, it actually also predicts a race, but that's actually a false race. As I've said, there is no predictable race in the example on the right. However, as I've said before, we do actually have a method of filtering these out. So I can't really go into the details of that because we don't really have that much time, but we took, so doesn't commute is our prior work, and we took it has this method of vindication that is able to verify whether a race is real or not. And we took that and extended it to be able to verify weak dependently precedes races. And in fact, we can filter out this false race so that we don't report it. Now, finally, I want to talk about results. So we evaluated our programs on the DiCapo 2009 benchmarks. So these are real-world programs that have been benchmarked. And just to show you the scale, some of these programs have up to 14 billion events in them. So things like writes, reads, lock, acquires, and releases, and so on, up to 14 billion in a single program. And some of the programs have up to 106 threads under our configuration. So really large-scale programs. And we built everything on top of the Roadrunner framework, which is the same framework that Fast Track uses. So when we look at the results, one thing we can compare is weak causally precedes and strong dependently precedes. So these are both sound race detection methods. And you can see, especially with Tomcat and Zalen, that strong dependently precedes does find more races than the prior work. We can also look at the non-sound ones. So doesn't commute and weak dependently precedes are both methods that are not sound. And if you look at the results, you can see that, again, especially with Tomcat and Zalen, weak dependently precedes finds a lot more races than DC. Now, of course, not every race weak dependently precedes finds is a real race. So we also went ahead and verified all of these races using our tool. And what we find is that even after the process of verifying these races, weak dependently precedes is the number of real races is still a lot larger than DC. So to recap everything, we have two new methods of finding data races. Strong dependently precedes, which is a sound method that finds no false races and beats prior work in terms of race detection capabilities. And weak dependently precedes, which is a complete method, meaning that it finds all races that are knowable from a single execution trace. It also finds false races, but we do have a method of filtering those out. Thank you for coming to my talk. I'll now take questions.
Please queue for the questions. So I have got a speculative question. Mm-hmm. If you put all reads and writes in acquire release, you don't have data races, but you still have you could have logical data races where you read a value, you augment it, you write it back. Can you imagine that your tool could be extended to catch those?
It's definitely possible that if you had, for example, if you had some sort of like programmer annotation that defines what constitutes a like region of the code that should be like kept consistent in a way, you could definitely design a tool that would catch that sort of races. And that's not just for our tool. You could do that with happens before or weak causal precision and all the prior work as well. But as far as I'm aware, there hasn't been really research into that.
Isn't a function call such an annotation of something that should be consistent? And then you would have it in your traces, I mean.
You could definitely do that, yes. But as I've said, I'm not aware of any research that has been done, at least using these methods.
Hey, thanks for the talk. I work at Google. I have a lot of code. I would like to try this. Is that possible?
Yes, our implementation is based on Java. So if you have Java code, you could definitely, as long as you're not using like any like loader magic, you can use our tool to actually detect races in your program. There are some things that we can't detect. For example, if you're doing any like calls to the unsafe libraries of Java, or if you're doing any foreign functions, we can't detect those. But everything that's actual Java code, we will be able to detect.
Cool. So where can I find your tool?
So we do have our implementation available on GitHub. You can find the link on our paper, and if you'd like, we can actually discuss offline how you can get it.
Cool.
And I'd be happy to, if you want to use it, I'd be happy to help you set it up if you have any questions.
Any more questions? In that case, I suggest we thank the speaker and we race for lunch.